Okay, continuing on today with our Laplace transform playlist, we're going to do something pretty interesting here. We're going to start going over inverse Laplace transforms. So that basically means we're kind of doing the process in reverse, and there's not too much to explain about it. So we're going to get into examples pretty quick, and I have one here. Just notice this different notation, kind of like just like arc sine, where we have this -1 to show that we're finding an inverse here. Now you notice in all the examples we did previously, we started with functions in t, and we transformed it into these functions in S. And so this was just our regular Laplace transform, taking us from t to S. Now this whole process starts to become really important when we start looking at differential equations. So when we're solving a differential equation, let's say we start with some equation in t, and what we do is we use this method of Laplace transforms to convert it into some function in S, where hopefully it's going to be easier to deal with. Kind of like an integration where we do a substitution, and the substitution is going to hopefully make the problem easier. We take our function into this S world where hopefully we can solve it, but then our solution still needs to be in t, kind of like in an integral, like in an indefinite integral where we have to bring it back to x. Well, here we can't just leave our answer in S, we need to convert it back to t. So in order to get our solution back into some function in t, and so that's why we need the inverse Laplace transform in order to undo what we did previously in this Laplace transform step. So getting back to how it works in practice, we have a problem like this where we want to find the inverse Laplace transform of 3 over s squared plus 9. So there's a few keys to being able to do these problems. So I think the most important thing is knowing your Laplace transform table or having a reference to a Laplace transform table handy. So it's basically just familiarity with everything we went over in the previous videos to get to this point. And so really what we're trying to do is we want to recognize this as one of the formulas we already know, or is there some algebra we can do in order to get it into that form of a formula we know. So here we're starting with a pretty easy example. We have this formula for the Laplace transform of sine of at that we found a few videos back. And so the formula we found for this is just the same thing as a over s squared plus a squared. Well, in this example here, I don't have to change much. I can just take this 9 and let's just write this as 3 squared. And then at this point, what we have here is exactly this. If the a value is 3, we're exactly in this form. So what we can do is go back to f of t, because f of t is what we want to get back to the t world, right? So we want some function in t. So if we know a is 3 and we have this is going to be just sine of 3t. So let's do one more relatively easy example. Let's say we want to find the inverse Laplace transform of just 1 over s to the 4th power. For this, we have a pretty good formula we can use from our Laplace table, and it's just going to be something, let's look at t to the n, where n is an integer. And the formula we have for this is n factorial over s to the n plus 1. So just matching the exponents here, if we say this n plus 1 value equals 4, then our n value equals 3. So if n is 3, let's just look at the Laplace of t cubed. That's going to be 3 factorial or 6 over s to the 3 plus 1 or s to the 4th. But the trouble we have here is we have a 6 here in the numerator, we have a 1 here. Well, I can change that real easily just by forcing this to be a 6, but I don't want to change it, so I could bring 1/6 up front. Just like we established with Laplace transforms, we can factor out a constant or distribute it back in. But again, just doing this process in reverse, you can think of it like taking the Laplace inverse on both sides, right? I know that's sloppy, but if you do that, what you end up with is our f of t value here, which is t cubed. So if this thing is t cubed, we can just write this as t cubed over 6. Okay, I'll do one harder example before we finish up. So okay, here we have this Laplace transform here, and the thing I noticed, this doesn't really look like any formulas that I know, just looking at all this. And you could do it a couple ways. I think what I want to do to start, I can actually factor -4 out of this and rewrite it. So what's going to happen is this is going to become s minus 4. And for this denominator, I could actually complete the square, or I could just factor it. So I think I'll just factor it. So this is going to become, I can write this as s minus 5 times s minus 3. But now for this thing, just like when we encounter this with an integral, we can do partial fractions on this. So we can do this using the cover-up method. So we'll write it over here. And so splitting up the denominator, we'll have this as a over s minus 5 and b over s minus 3. So with the cover-up method, we'll start here. We'll plug in, if this is s equal to 5, cover up this term. Plugging in the numerator, we have 5 minus 4, 1. And then here, plugging in 5, we're going to have just a 2 there. So our a value is 1/2. And then for this other term, what I can do is set my s equal to 3, cover this up, plug this in here. Now, in the numerator, 3 minus 4 is going to give me a minus 1. And then here, 3 minus 5 is going to give me minus 2. But minus 1 over minus 2, that's just 1/2. So now taking this and putting it back into the Laplace transform, what I'm going to do actually is I can actually split this up into 2. Because we have the plus sign here, and we have the same properties that we have with the regular Laplace transform. So we can write this here. I can write this as 1/2 over s minus 5. And here I'll distribute the minus 4. We'll have the inverse Laplace. This is still 1/2 over here, and this is going to be s minus 3. But then from here, I can factor the half out front here, factor the half out front here, and I can actually factor this minus 4 up because we have minus 4 on both these, so it's going to be the same minus 2 on both these. So what I'm going to do is write this minus 2. We'll have the inverse Laplace here of just 1 over s minus 5. And then as we factor out minus 2, this is going to be just a plus, and this is going to be inverse Laplace, and this is going to be 1 over s minus 3. But now here we've got a familiar formula for each of these that we can use. This is the same formula. What we can look at is something we did, one of the first videos we did, I think it was Laplace e to the at, and this is going to be the same thing as 1 over s minus a. So in this case here, our a value would just be 5, and in this case here, our a value would be 3. So finishing this off, we'll have our minus 2 out front, but this thing is going to be the same thing as this f of t when a is 5. So this is going to be e to the 5t. And then for this other one, same thing, using this formula, this is going to be e to the 3t. Just circle it, and that's it. So there you have it, introduction to the inverse Laplace transform. In the next few videos, we'll just do a bunch more examples. Thanks everyone for watching today. Have a good day.